Thank you for your kind introduction. Welcome everybody to the season number 3 of this webinar entitled PV Plant Project Development, Design, Solar Resource, EPC and Contracts and Warranties. The summary of this presentation is shown on this slide. Point number 1, introduction to PV plants. Number 2, review of steps in a PV plant project. Point number 3, PV project contract structure. Number 4, solar resource and energy production. Point number 5, point of interest. And finally, number 6, good and bad practices. As an introduction to this presentation, photovoltaic plants can be classified into 2 main groups, grid-connected and standalone. In addition, each group can be divided in PV plants grid-connected with self-consumption and without self-consumption, and PV plants standalone with DC loads, with AC loads, and with AC and DC loads. According to their location, photovoltaic plants can be classified into photovoltaic plants of ground level, terrestrial or floating, PV plants on rooftop, and building integrated, BIPV. This slide shows several examples of grid-connected photovoltaic plants on ground level, terrestrial and floating, on rooftop, and building integrated photovoltaic. This is the solar photovoltaic value chain that involves the PV plants. From the point of view of the material use, the amount of the materials required for a 1 megawatt photovoltaic plant is presented. From the social economic point of view, the solar PV industry employed 3.6 million people worldwide in 2018, and this number is expected to rise further than 80.7 million people by 2050. As an example, distribution of human resources and occupational requirements along the value chains for a 50 megawatts photovoltaic plant is presented. Current photovoltaic plants must have the capacity to manage the electrical power generated, both active and reactive power. The active power presents the control of the frequency of the utility grid, and the reactive power control presents the static voltage support of the utility grid and the dynamic voltage support of low voltage right-through. Due to the use of power electronics elements, photovoltaic plants have a higher level of control than conventional electric power plant. This slide shows an overview of a photovoltaic project, its complexity, and the different steps to be taken to carry it out. The final responsible of this project must execute, supervise, or subcontract all the phases, and carry out the coordination with the investors or promoters of the photovoltaic project. The development of a photovoltaic project can be divided into several stages. The stage 1, the site identification, contains the identification of potential sites, funding of project development, and the development of a rough technical concept. The stage 2 is the pre-feasibility study that contains the assessment of different technical options, an approximate estimation of costs and benefits of the PV project, the permitting needs, and the market assessment. The stage 3, feasibility study and preliminary PV project, contains the technical and financial evaluation of preferred option, the assessment of financing options, and the start of permitting process. The stage 4 is the financing and contracts stage that contains these tasks: the permitting, the contracting strategy, supplier selections and contract negotiation, and the financing of projects with the bank or a financial institution. The stage 5, the detailed design and the PV project phase, is the preparation of detailed design for all relevant lots, the preparation of project implementation schedule, and the finalization of permitting process. The stage 6 is the construction of the PV plant that involves this task: the quality assessment testing on-site plan and the construction supervision. The stage 7, commissioning, contains this task: the performance testing and the preparation of as-built design if required the project. The stage 8, the operation and maintenance of the PV plant, contains this task: developing of tasks according to O&M procedures, the spare parts and suppliers management, and monitoring task. And finally, the stage 9 is the dismantling of the PV plant that contains this task: the management of all and out of service equipment, and finally, the land restoration. Entering the contractual structure of a photovoltaic project, the equipment procurement contract is related with the acquisition of the equipment of the PV plant. The scope of this contract is the equipment models, equipment technical specifications, the product audit and the factory process audit of the manufacturer, the acceptance criteria, logistics, Incoterms and delivery time of the equipment, condition of use, compliance with the regulation and the standards of the equipment, the documentation, and the price and payment method. The technical specification that contains this contract is the factory quality system, the certifications, and its traceability. The testing involved in this contract is the factory testing, the pre-shipment testing, the on-site at plant reception testing, and on-site mounting testing, and finally the commissioning testing, and the warranties that affect this contract is the product warranty and performance warranty. The possible risk in the equipment procurement contract are the indefinition or insufficient technical specifications to ensure the choice of suitable components, the inadequate testing of components to verify manufacturing deviations of the product, and the absence or non-definition of component acceptance criteria. The EPC contract, engineering, procurement, and construction contracts are the most common form of contracts used to undertake construction works by the private sector on large scale and complex infrastructure projects. Under an EPC contract, a contractor is obliged to deliver a complete facility to a developer who needs only turn a key to start operating the facility. Hence, EPC contracts are sometimes called turnkey construction contracts. So the scope of contract in a PV project are the solar resource and energy product estimation, the design and engineering, the landing preparation, the construction and mounting, definition of monitoring, definition and operation and maintenance procedures, definition of commissioning procedures, safety and surveillance of PV plants, and spare part list. The technical specification of the EPC contract contains the design and technology of PV plants, the selection and quality specification of the equipment, the product warranties, and the product certifications. Testing involved in this contract are the technical inspections, the quality assurance, the product testing, and commissioning. And warranties that affects this contract is the PV plant performance, the product operating, the availability of the PV plant, and the O&M warranty. There are several kinds of possible risks in the EPC contract. From the point of view of design, the possible risk of the EPC contract are the no consideration of the evaluation of the solar resource in the long term, because the solar resource is based off 1 year, in the initial year. The no consideration of statistical studies in the estimation of the PV plant electricity generation, the underestimation of the degradation of PV modules and its effects on the estimation on their long-term behavior, and the no consideration of the PV plant availability when evaluating the estimation on energy production. From the point of view of the construction, the possible risks in the EPC contract are the indefinition of tasks and responsibilities in the contract agreement with the rest of the contract, indefinition of transport and assembly guidelines for PV modules, unsuitable procedures when unpacking components and incorrect handling during construction or installation, and lack of supervision during the construction or installation stage that ensures quality criteria. And finally, from the point of view of commissioning, the possible risks in the EPC contract are the inadequate visual inspection process during the provisional or final acceptance stage of the PV plant, the incorrect definition of the performance rating value of the PV plant, the indefinition of the performance rating measured and guaranteed at the final acceptance of the PV plant, the absence of equipment specifications and data collection for the calculation of the performance rating during provisional and final acceptance of the PV plant, and the absence of documentation of the PV plant after starting operation. The operation and maintenance contract is another key element in the contract structure of the photovoltaic project. The scope of this contract must contain the predictive, preventive, and corrective maintenance, the warranty claim and the spare part management, the PV module cleaning and vegetation control, the safety and surveillance task of in the PV plant, the monitoring and the production and operation and maintenance reports. The technical specifications of this contract is the instructions and users manuals of the equipment and the O&M procedures. Testing involved in this contract are all the operating and maintenance procedure after maintenance action. And the warranties that involves this contract is the PV plant performance, the product operating, the availability, and the operation and maintenance warranty. The possible risk in the O&M contract are the inadequate monitoring system for the detection and identification of faults in the PV plant, the unavailability of devices for detecting defects not visible for the human eye during preventive maintenance tasks, for example, the thermographic equipment, the indefinition of PV plants performance indicators warranted in the O&M contract, the absence of equipment specifications and data collection for the calculation of the performance rating during the O&M stage, the absence of a maintenance clause for the sensor and monitoring system, and the absence of a specification of cleaning frequency of PV modules or low frequency. A power purchase agreement, PPA, or electricity power agreement, is a contract between two parties, one which generates electricity and one which is looking to purchase electricity. The PPA defines all of the commercial terms for the sale of electricity between the two parties, including when the project will begin commercial operation, schedule for delivering of electricity, penalties for under-delivery, payment terms, and termination. A PPA is the principal agreement that defines the revenue and credit quality of a generating project, and is thus a key instrument of project finance. There are many forms to PPA in use today, and they vary according to the needs of buyers, sellers, and financing counter. So, the scope of PPA contract is the estimation of energy production, the interconnection with grid, the prediction of energy production, feed-in tariff, payment form, and energy measurement. The technical specifications of the PPA contract are the electric market regulations and the certificate of origin of energy if required, and the warranties, the supply energy, and the origin of the energy renewables. The estimation of energy production in a photovoltaic project is based on the solar resource of the selected location contained in the radiation databases and the technical specification of the photovoltaic installation. Normally, the radiation databases present a typical meteorological year, a fictitious year generated synthetically with the most common values in the location. There are several methods for producing the typical meteorological year that are inserted inside the databases. All this information is collected by the PV system software simulation that generates the energy product estimation. However, in order to estimate the energy production with a high added value and for a correct design of the photovoltaic plant, it's necessary to carry out an analysis of the loss factors. There are several types of loss factors: the radiation loss factors, the DC side loss factors, and the AC side loss factors. Radiation loss factors are referring to the part of solar radiation that exists at the location, but does not reach the photovoltaic modules. Radiation loss factors include the angle of incidence, which is related to the effects of radiation reflection on the PV module surface. The soiling, which is related to the dust and dirt deposited on the module surface and depends on the climate and type of the terrain. Shading effects, both near shadings or outer shadings and far shadings that is generated by the horizon line. The loss factors of the DC side are related to the behavior of the photovoltaic modules and their interconnection. The most important effect on energy production is the cell temperature of the photovoltaic modules due to the nature of the photovoltaic conversion. There are various methods for calculating this loss factor. Each photovoltaic system simulation software has one of these methods implemented, which normally take into account the incident in radiance, ambient temperature, and wind speed. The irradiance loss factor takes into account the effect that a photovoltaic module is characterized by certain irradiance condition, 1,000 per square meter, but its behavior is not the same for all irradiance values. In fact, this factor can be a gain, since in other irradiance, the photovoltaic module can behave better. The mismatch loss factor considers the effect of having different parameters of the PV modules interconnected due to manufacturing tolerances and parameter dispersion. This means that the sum of the powers of all the photovoltaic modules placed in the same operating conditions is not the total power of the photovoltaic generator. This difference can be seen between the green line and the black line in the figure on the right side of the slide. The ohmic loss factor takes into account the voltage drops in the plant cabin. All the wiring can be considered as an equivalent resistance, which can be calculated by knowing the section and the length of each cable. The MPPT loss factor refers to the efficiency of the maximum power point tracking system implemented in the PV inverter. Currently, the systems have an efficiency of 99% or higher, so this loss factor can be neglected. The loss factors related to the AC side refer to the electrical energy converted into alternating current. The most important factor is the efficiency of the DC-AC conversion that takes place in the PV inverter. This efficiency depends on the voltage level and the input DC power level. The concept of efficiency curves is updated by efficiency maps. Additional losses may exist due to over or undersizing of the inverter with respect to the photovoltaic field, which may place the input DC voltage and current outside the operating range of the inverter. In the case of existing low voltage, medium voltage step-up transformer, the intrinsic losses of the transformer, copper losses and iron losses, must be considered. These losses depend on the operating mode of the transformer in accordance with its efficiency curves. The transmission line loss factor must be considered in the case that the transformation center is in a distant substation. Transmission line losses might be borne by the PV plant depending on the applicable legislation, PPA, etc. With the solar resource of the location, the technical specifications of the photovoltaic plant, and the calculation of the loss factors, the photovoltaic system calculation software can generate a production estimation. However, it's often necessary to obtain a probability distribution of energy production based on a normal distribution. This normal distribution has an average production value equal to the software's calculation, and a standard deviation associated with the variability of the different factors that influence the energy estimation. The energy estimation is complete with the analysis of long-term production. For this analysis, a final loss factor is taken into consideration, which is the power degradation of the photovoltaic modules. As a point of interest, it's necessary to consider the design strategy of the photovoltaic plant in the first stages of the photovoltaic project. it must be considered that there can be different strategies: higher levelized cost of energy, higher internal investor return, lower initial investment, higher specific production, higher ground coverage ratio, and other strategies like experimental installations, emblematic projects, etc. These strategies depend on the particular conditions of the photovoltaic project. The main conditions being the following: fixed cost, not related with the energy production. I mean, all costs different to PV modules. The location, considering assembling costs, transport of equipment, and labor cost. Financing conditions, and technical or legal limitations. This is an example of a previous study for a fixed installation, varying tilt and pitch. This type of a study can be very useful to identify possible designs or distribution options of the photovoltaic field, maximizing production and ground coverage ratio. It's interesting to consider the number and type of failures that occur in photovoltaic installations, not only the number of events, but their effect on the interruption of energy injection. These graphs show the percentage distribution of failures, the number of events that occur, and their effect on energy. As can be seen, the largest number of failures is related to the inverters, although the largest loss of energy is related to failures on the AC side. In this slide, we can see some examples of good and bad practices about some aspects related to the construction and operation of a PV plant. In the present slide, we can see the PV modules transport in an incorrect way and in a correct way. The transport of the module from their unpacking to their final installation in the PV generator. This is another examples of the PV module transport and installation, final installation in an incorrect way and correct way. The PV modules installation must follow a program of the installation of the photovoltaic modules according to the arrival and reception times at the PV plant. If not, modules can appear in the middle of the PV installation and can suffer these consequences. The PV modules cleaning must voided with a correct cleaning program. Presence of it or not programming or execution of the cleaning in the photovoltaic generator when it's necessary can provoke these situations. Related to the structures, a lack of anti-corrosion treatments and preserve of corrosion can be a perceivable defect. The different and incompatible metals is not isolated from each other, e.g. aluminum and stainless steel, can cause problems in the form of galvanic corrosion. The grounding must done in a correct way with the appropriate marking of the wiring of the ground earth. In case of mounting of structures, it must be done in the appropriate way with the appropriate materials. The anchored systems and torque must be the correct. The wiring must be identified as its polarity and the name of its circuit. Looping must be avoided in all cases. The wiring connection must be done in a correct way. It must be avoided the incompatible connectors for the connection. Placing and maintenance of the connection box can lose the protection, the IP protection level of the connection boxes, with a potential electric risk. Related to the solar trackers, the status of the solar trajectory tracking of all the solar trackers must be checked to ensure the correct operating of the solar tracker. Installation of the PV inverters must be done in accordance with its specifications, with the respecting the space and the clearance for the cooling system, and must be checked the state of the filter cleaning for avoiding malfunctions. In case of outdoor PV inverters, the installation of these inverters must be done in a suitable enclosure with a IP degree protection adequate and with a protection against the direct sunlight. Placing the sensor of monitoring system, especially the irradiation sensor, must be done in an adequate way in order to obtain adequate data for further analysis. Related to the civil works, foundations of the supporting structures or solar trackers must be done according to their specifications and the geotechnical conditions of the ground. An adequate drainage system and rainwater network, its condition and its conservation can avoid potential risks for the PV installation. The location of the photovoltaic generator, structures, and/or trackers must be done considering other constructions and its settings. Finally, vegetation control in the PV installation is necessary in order to avoid possible problems in the PV modules and maintain a necessary cleaning in the internal path of the PV installation. Thank you very much for your attention.
Thank you, Hilde. It was a very nice presentation and with so many examples. Now we are going with the questions. There are only 3, I see, or 4. Okay, this one, the first one is from Antoine, from Thea. According to your experience, what is the main parameter influencing the decision to launch a PV project? This is the first one.
Okay, I hope that you hear me okay?
Yes.
Okay. Well, this is a very interesting question, because the key point is the complete conditions related to the initial investment of the PV installation. This is a great number of factors that can be viable on an unviable PV project. In these cases, the financial costs are a key factor. Without any kind of financial, it's impossible to execute any PV project. And the control of the initial investment and the internal investment return is a key important. So the economical parameters are key points to initiate or to mark the success of the PV project. In this case, the reduction of the materials and components and optimization of this cost related with the energy production can become decisive in the successful of the PV project extension.
Okay, thank you. There is another question from Vinay Kumar. Which site is more efficient to install a PV plant?
Well, it's a wide question. If you allowed me, the question will be, what is your conditions that you have for initiating the PV project? Because related with the before question, your conditions is marking the possible successful or failure of the PV plant. And if you have a great location with a great value for irradiation, but your cost for transport, for labor, for any other costs are very, very expensive, this location is not suitable for a great installation. In fact, if you have a location with a poor radiation, but with a fixed cost, lower fixed cost, this PV project can be possible. Even the figures are not great figures, but it's suitable for your investment.
Okay. Another question from Antoine. Which loss factor do you use as default value for modules mismatch losses?
Yes, an interesting question again. CENER is using our own algorithm to calculate this loss factor using the IV curve and the other parameters related with the location. We are abandoning the idea of defect value because it is not suitable for many situations. And it strongly depends for the technology of the PV modules, for the connection of the PV plants, the strings, the serial and the parallel connections in the configuration of the PV generator. So this calculation is own of CENER.
Okay. Another question from Alexander Mifsud. How is loss factor for a dirty panel? With soiling.
This point is specifically under study because there is it's not a clear determination of the loss factor, the soiling loss factor, because it strongly depends from the terrain, from the climate, and from the type of the material that is deposited on the surface of the PV modules. So there are a lot of studies in process, including at CENER. So the answer is not it's not clear for the moment.
Okay, thank you.
Thank you. Another question is from Tum Nithin Chandra. What are the general procedures followed for operational maintenance in PV systems?
Well, you know, it's not okay. It's obviously that there is a task that is common for all PV installations, but the operation and maintenance procedure is a specific document generated with the constructor and the O&M responsible, and it's defined by both parties. General maintenance is like the maintenance of the equipment, the procedures of the preventive, predictive and corrective maintenance, and obviously the management of the suppliers and the spare parts in the operation. Maintenance obviously includes the management of the monitoring data and the generating the reports according to this data that it could be necessary for the financial entity of the bank or the promoters or owners of the PV plant.
Yes, there is another question. If the AC/DC converter has the highest percentage possible failure rate, what components really fail inside?
Well, it depends on the models of the PV inverters, and there are a lot of possibilities. The PC boards will be the most failure in inverters. So the protections, it's not protections. This could be, but it strongly depends on the PV inverter, of the model of the PV inverter. So each model, each mark has your own strengths and weakness in their equipments. So it is not a global answer to this question.
Yes. Another question from Javier Lopez. You mentioned a higher EPC-O&M as a strategy for PV installations. What would be the benefit of that strategy? My understanding is that the usual target is finding the lowest EPC-O&M possible. Thank you.
Well, the strategy marks the initial conditions, or especially the financial conditions of the PV projects, or even the disposal of the terrain, because this cost depends strongly of the PV, the weight of the PV project in all the PV plant and on all the PV project. So the fundamentals of the objective of the PV installation is your objective to minimize or maximize your wake point. In this case, the levelized cost of energy is a great point, but it's not the only point in this case.
More questions. One from Somes, from MCAS. Is there a general convention for sizing inverters for the PVs?
This is a great question. This is a point of an interest too, because the PV inverter must match with the electrical conditions of the PV generator, but we must take into consideration that power of PV modules will suffer a degradation. So this power is not the same along the time. So higher value of PV power, DC power, is recommended for a determined PV output of AC PV output. So the ratio of the power of DC power, AC power, it will be a ratio of 1.25 as a reference. But all values that can increase this value, if it is possible, is recommended, because losses for moments of higher production that could limit the production of the inverters are very small moments along the year. So all the periods, if you have a great amount of DC power, could be operating the PV installation with a higher value of production. So a reference value, orientative value of 1.25 ratio between DC power and AC power, it could be interesting.
Okay, I think this is enough. And the last question is, what are the main defects observed in recent PV installations? From Antoine.
There is a lot of defects, depending on the moment of this the moment of the operation or maintenance of this PV installation. With a grid operation and maintenance procedures, the PV plants has very low events of failure. But if the operation and maintenance is very poor, it could be a mess in every type of in every part of the PV installation. For example, the PV module, the state of the wiring. For example, the simple that the maintenance of wiring of the civil works. In case of new PV installations, all the efforts are focusing on the detection of the PV modules before its installation by the electroluminescent testing or thermography testing on this type of tests, while in pre-shipment tests or on-site tests. This could point to the quality assurance and avoid these possible defects on the PV modules that affected in the production and could be affected in a long term, not in the first moments.
Okay. If there are no more questions, we can finish the session. You can contact Hilde. Thank you very much, Hilde, for the presentation. To end with the webinar, I would like to give the microphone to the coordinator of the project Jam2Ester, Ryan. Dr. Ryan Azopardi from MCAS Energy. He can introduce the project and his institution.
Okay, so I'm Brian Azopardi. Hello. I am from MCAS Energy, and we are leading this project together with Sener, who are doing excellent workshop deliveries, one every day this week, which are very interesting. Together with partners CEA and the University of Manchester, and the project basically is involves a number of activities where the participants who are currently following us online can also register and benefit from this. These include from schools. We have a school coming on in March, which we will be advertising on, disseminating on this soon, and other activities and stakeholders within the area of photovoltaics. We basically are interested in a wide range of integration of photovoltaics research teams, from testing, on-site testing, to systems integration, to policy making and markets, including also energy and water nexus related with photovoltaics. We are happy to collaborate with you. I'll stay short. I'll just say thank you very much for Sener to keep these workshops very, very well attended and very interesting, the topics. And our next school, actually this is just a hint of what we will have in the next school, because our next school will be also related with these type of topics on the photovoltaic testing of that we've seen in the first 2 days as well. Photovoltaics panels testing or solar cells testing, etc. So thank you very much, Eugenia, and well done for this organization.
Thank you, Ryan. Now I am going to close the session. I just want to remind you that we are going to have another webinar tomorrow, and the topic of the webinar will be about potential induced degradation. So we will see tomorrow. Thank you very much. Thank you, Hilde, for the presentation, and thank you, Brian.
Thanks a lot. Thanks a lot, Eugenia. It was very nice. I enjoyed it as well. Thank you. Bye-bye.
See you tomorrow. Bye.
See you. Bye.
See you.